energy. I want to discuss the solar thermal collectors. My today's lecture, I will discuss what is the solar thermal collectors, the classification of the solar thermal collectors. It is classified by two, that is non-concentrating or the stationary collector and the concentrating collectors. And in today's lecture, I mainly focus on the non-concentrating or the stationary collectors like the flat plate collectors, evacuated tube collectors, and the compound parabolic collectors. Now come to the point at what is the solar thermal collector. The solar thermal energy is a form of energy and a technology for harnessing the solar energy to generate the thermal energy or the electrical energy for use in industry and in the residential and the commercial sectors. The solar thermal collectors are a special kind of heat exchangers that transform the solar radiation energy to internal energy of the transport medium. The major component of any solar system is the solar collector. This is a device which absorbs the incoming solar radiation, converts it into the heat, and transfers this heat to a fluid, usually air, water, or well, flowing through the collector. The solar energy thus collected is carried from the circulating fluid either directly to the hot water or space conditioning equipment or to a thermal energy storage tank from which this can be drawn for use at night and or the cloudy days. Now the classification of the solar thermal collector, it is mainly classified by two types, that is the non-concentrating or the stationary and the concentrating. A non-concentrating collector has the same area for the intercepting and for absorbing the solar radiation, whereas a sun-tracking concentrating solar collector usually has the concave reflecting surfaces to intercept and focus the sun's beam radiation to a smaller receiving area, thereby increasing the radiation flux. Now the non-concentrating or the stationary collectors are divided by three types, that is flat plate collectors, evacuated tube collectors, and the compound parabolic collectors. The flat plate collectors are mainly defined with respect to the which type of carriers, heat carriers are in that collectors, that is the liquid flat plate collectors or the air flat plate collectors. The liquid flat plate collectors are again divided by the non-glazed or the glazed collectors. The concentrating collectors are divided by four types: the parabolic trough collector, linear Fresnel reflector, parabolic disk system, and the central receiver or the heliostat field collector. Today in this lecture, I will describe the non-concentrating or the stationary collector only. Now the first type of non-concentrating collector is the flat plate collector. The flat plate collectors are the most common solar collector for the solar water heating systems in homes and the solar space heating. A typical flat plate solar collector is shown in the figure below. A typical flat plate collector is an insulated metal box with a glass or plastic cover called the glazing and a dark color absorber plate. These collectors heat liquid or the air at the temperatures less than 180 Fahrenheit. Flat plate collectors are used for the residential water heating and hydronic space heating insulations. When the solar radiation passes through a transparent cover and impinges on the blackened absorber surface of the high absorptivity, a large portion of this energy is absorbed by the plate and then transferred to the transport medium in the fluid or the air tubes to be carried away for the storage or use. The underside of the absorber plate and the side of the casing are well insulated to reduce the conduction losses. The liquid or the air tubes can be welded to the absorbing plate, or they can be an integral part of the plate. The liquid or the air tubes are connected at both ends by the large diameter header tubes. The transparent cover is used to reduce the convection losses from the absorber plate through the restraint of the stagnant air layer between the absorber plate and the glass. It also reduces the radiation losses from the collector as the glass is transparent to the shortwave radiation received by the sun, but it is nearly opaque to the long-wave thermal radiation emitted by the absorber plate. This is the greenhouse effect. For the household water heating and the swimming pool heating, the liquid flat plate collectors are used, and for the space heating, the air flat plate collectors are used. The liquid flat plate collectors heat liquid as it flows through the tubes in or adjacent to the absorber plate. The simplest liquid systems use the potable household water, which is heated as it passes directly through the collector and then flows to the house. The unglazed liquid flat plate collectors, this is mainly used in the solar pool heating. These collectors are most commonly used the unglazed solar technology in the United States mainly. The figure shows the unglazed solar collectors. One is the tube-on sheet collector and another is the serpentine plastic pipe collector. These devices often use the black plastic tubular panels mounted on a roof or the other support structure. A water pump circulates the pool water directly through the tubular panels, then returns the water to the pool at a higher temperature. Although it is used primarily for the pool heating, these collectors can also preheat large volumes of water for other commercial and the industrial applications. The second type is the air flat plate collectors. The air flat plate collectors are used primarily for the solar space heating. The absorber plates in air collectors can be metal sheet, layers of screen, or the non-metallic materials. The air flows past the absorber by using the natural convection or a fan. Because the air conducts heat much less readily than the liquid does, less heat is transferred from an air collector's absorber than from a liquid collector's absorber, and the air collectors are typically less efficient than the liquid collectors. Now the flat plate collectors are usually permanently fixed in position and require no tracking of the sun. The collector should be oriented directly towards the equator, facing south in the northern hemisphere and north in the southern. The optimum tilt angle of the collector is equal to the latitude of the location, with angle variation of 10 to 15 more or less depending on the applications. Their major purpose is to collect as much solar energy as possible at the lower possible total cost. The collector should also have a long effective life despite the adverse effects of the sun's ultraviolet radiation, corrosion and clogging because of the acidity, alkanicity and the hardness of the heat transfer liquid. freezing of water, or the deposition of dust or moisture on the glazing, and the breakage of the glazing because of the thermal expansion, vandalism, or other causes. These causes can be minimized by the use of the tempered glass. Now the components in the flat plate collector. The first component is the glazing. It is one or more sheets of the glass or other diathermoous radiation transmitting material, just like a glass or plastic frames are used. Glass has been widely used to glaze the solar collectors because it can transmit as much as 90% of the incoming shortwave solar radiation, while transmitting the virtually none of the long wave radiation emitted outward by the absorber plate. Glass with low iron content has a relatively high transmittance for solar radiation, approximately 0.85 to 0.90 at normal incidence, but its transmittance is essentially 0 for the long wave thermal radiation, that is 5 to 50 micrometer, emitted by the sun heated surface. Plastic films and the sheets also possess the high shortwave transmittance, but because of the most usable varieties also have transmission bands in the middle of the thermal radiation spectrum, they may have long wave transmittance as high as 0.40. The plastics are also generally limited in the temperatures they can sustain without deteriorating or the undergoing dimensional changes. Only a few types of plastic can withstand the sun's ultraviolet radiation for the long periods. However, they are not broken by hail or stones, and in the form of thin films they are completely flexible and have the low mass. The commercially available grades of window and the greenhouse glass have normal incidence transmissions of about 0.87 and 0.85 respectively. For the direct radiation, the transmittance varies considerably with the angle of incidence. Anti-reflective coatings and the surface textures can also improve the transmission significantly. The effect of dirt and dust on the collector glazing may be quite small, and the cleansing effect of an occasional rainfall is usually adequate to maintain the transmittance within 2 to 4% of its maximum value. The glazing should admit as much solar irradiation as possible and reduce the upward loss of heat as much as possible. Although the glass is virtually opaque to the long wave radiation emitted by the collector plates, absorption of that radiation causes an increase in the glass temperature and a loss of heat to the surrounding atmosphere by radiation and convection. The second is the tubes and fins or the passage. To conduct or direct the heat transfer fluid from the inlet to the outlet, it is mainly used. The type M copper tube is mainly used as a tube or fins or the passage. There are 4 types of tube or fins or passages are used in the flat plate collectors, such as the serpentine, the metal tubing soldered to the metal sheet, the parallel tube, the tube formed in the metal sheet, and the tickle type corrugated sheet is also used. The flow passage conduct the working fluid through the collector. If the working fluid is a liquid, the flow passage is usually a tube that is attached to or is a part of the absorber plate. If the working fluid is air, the flow passage should be below the absorber plate to minimize the heat losses. The flat plate collectors can involve the liquid or the air heat transport. Water is one of the common options as the liquid fluid due to its accessibility and the good thermal properties. It has the relatively high volumetric heat capacity, and it is incompressible or almost incompressible. It has a high mass density also. One disadvantage of water is that it freezes during the winter, which can damage the collector or piping system. This can be managed by draining down the collector at low solar inputs below the critical insolation threshold. Drain down sensors are often employed to monitor the system and to ensure the complete draining, as the pocket water freezing can cause damage. Refilling the system with water on the next morning also is not perfect. Possible air pockets in the collector can be a problem, blocking water flow and the decreasing system efficiency. The antifreeze mixtures can be used instead of pure water to alleviate the above said problems. The common antifreeze components are ethylene glycol or the propylene glycol. Those chemicals are mixed with the water, require the closed loop systems and the proper disposal due to the toxicity. Nominal antifreeze service life is about 5 years, after which it needs to be replaced. Air can be used as the transport fluid in some of the designs of the flat plate collectors. This option is better suited to space heating applications or the crop drying. A fan is usually required to facilitate the airflow in the system and efficient heat transport. Certain designs can provide the passive movement of the air due to the thermal buoyancy. Phase change liquids can also be used with the flat plate collectors. Some refrigerants are included in this group of fluids. They do not freeze, which eliminates the troubles explained above for the water, and due to their low boiling point can change from the liquid to gas as the temperature increases. Those fluids can be practical in setting where the quick response to rapid temperature fluctuations is needed. The third component is the absorber plates. The flat corrugated or the grooves plates to which the tubes, fins and the passes are attached. The plate may be integral with the tubes. The collector plate absorbs as much of the radiation as possible through the glazing while losing as little heat as possible upward to the atmosphere and downward through the back of the casing. The collector plates transfer the retained heat to the transport fluid. The absorbance of the collector surface for shortwave solar radiation depends on the nature and color of the coating and on the incident angle. Usually, the black color is used. However, the various color coatings have been for the aesthetic sense. By suitable electrolytic or the chemical treatments, the surfaces can be produced with the high values of solar radiation absorbance alpha and the low values of the long wave emittance, that is epsilon. Essentially, the typical selective surfaces consist of a thin upper layer which is highly absorbent to the short wave solar radiation but relatively transparent to the long wave thermal radiation, deposited on a surface that has a high reflectance and a low emittance for the long wave radiation. Selective surfaces are particularly important when the collector surface temperature is much higher than the ambient air temperature. An energy efficient solar collector should absorb the incident solar radiation, convert it to the thermal energy and deliver the thermal energy to a heat transfer medium with the minimum losses at each step. It is possible to use the several different design principles and physical mechanisms in order to create a selective solar absorbing surface. Solar absorbers are based on two layers with the different optical properties, which are referred to as the tandem absorbers. A semiconducting or dielectric coating with high solar absorptance and high infrared transmittance on the top of a non-selective, highly reflecting material such as metal constitute one type of tandem absorber. Another alternative is to coat a non-selective, highly absorbing material with a heat mirror having a high solar transmittance and high infrared reflectance. Nowadays, the commercial solar absorbers are made by electroplating, anodization, evaporation, sputtering, and by applying solar selective paints. Much of the progress during the recent years has been based on the implementation of the vacuum techniques for the production of the thin type of absorbers used in the low temperature applications. The chemical and the electrochemical processes used for their commercialization were readily taken over from the metal finishing industry. The requirements of the solar absorbers used in high temperature applications, however, namely the extremely low thermal emittance and high temperature applications, namely the extremely low thermal emittance and the high temperature stability, were difficult to fulfill with the conventional wet processes. Therefore, the large-scale sputter deposition was developed in the late 1970s. The vacuum techniques are nowadays mature, characterized by the low cost and have the advantage of being less environmentally polluting than the wet processes. For the fluid heating collectors, passages must be integral with or firmly bonded to the absorber plate. A major problem is obtaining a good thermal bond between the tubes and the absorber plates without incurring excessive cost of labor or the materials. The material most frequently used for the collector plates are copper, aluminium, and the stainless steel. The ultraviolet resistant plastic intrusions are used for low temperature applications. If the entire collector area is in contact with the heat transfer fluid, the thermal conductance of the material is not important. The figure D shows the use of extruded rectangular tubing to obtain a larger heat transfer area between the tube and plate. The mechanical pressure, thermal cement or brazing may be used to make the assembly. Soft solder must be avoided because of the high plate temperature encountered at stagnation conditions. The air or other gases can be heated with the flat plate collector, particularly if some type of extended surface, just like a figure E, is used to counteract the low heat transfer coefficients between the metal and the air. In the figure F, the metal or the fabric matrices or the thin corrugated metal sheets, as figure B, may be used with the selective surfaces applied to the latter when a high level of performance is required. The principal requirement is a large contact area between the absorbing surface and the airs. Next component is the headers or the manifolds to admit the discharge the fluids. Most flat plate collectors have two horizontal pipes at the top and the bottom called the headers, and mainly smaller vertical pipes connecting them called the risers. The risers are welded to the thin absorber pins. The heat transfer fluid, maybe water or the antifreeze mix, is pumped from the hot water storage tank or the heat exchanger into the collectors bottom header, and it travels up the risers, collecting the heat from the absorber fins and then exits the collector out of the top header. The serpentine flat plate collectors differ slightly from the hard design. The instead use of the single pipe that travels up and down the collector. However, since they cannot be properly drained of water, serpentine flat plate collectors cannot be used in the drain back systems. Next, the insulation. To minimize the heat loss from the back and sides of the collector, the insulation is used. As the absorber plate warms up, it transfers the heat to the fluid within the collector, but it also loses heat to its surroundings. To minimize this loss of heat, the bottom and the sides of the flat plate collector are insulated with high temperature rigid foam or aluminium foil insulation as shown in the figure. The insulation material should be dimensionally and chemically stable at high operation temperature. The thickness of the insulator should contribute to the structural rigidity. This investigation used the polystyrene as insulation because it is cheap, easy to find, and most importantly is the polystyrene has the good heat insulation characteristics. The materials most used for insulation are mineral wool, glass wool, and the foam glass. But wool can absorb the humidity from the atmosphere and the thermal insulation deteriorates substantially. So for this reason it should not be used. The polyurethane foam is used for low temperature applications and the styropor is used very rarely. The last component is the container or the casing. To surrounding the aforementioned components and keep them free from dust or moisture, etc., the container or casing is used. The flat plate collector must be insulated to reduce the conduction and convection heat losses through the back and side of the collector box. To reduce the both convection and radiation losses, a transparent cover protects the absorber, while conduction losses are limited with an efficient thermal insulation of the collector casing. It is also acting as the protection shield in adverse weather conditions. Normally it is made of sheet. The advantage of the flat plate collector is the easy to manufacture, it has the low cost, collect both beam and diffuse radiation, it is permanently fixed, no sophisticated positioning or tracking equipment is required, and the most important, it have the little maintenance. Come to the second type of non-stationary collectors, that is evacuated tube collectors, ETC. Conventional simple flat plate solar collectors were developed for use in sunny and the warm climates. Their benefits, however, are greatly reduced when the conditions become unfavorable during the cold, cloudy and the windy days. Furthermore, weathering influences such as the condensation and the moisture will cause early deterioration of the internal materials, resulting in reduced performance and the system failure. Evacuated tube collectors are particularly useful in those areas with cold, cloudy and the wintry weathers. Evacuated heat pipe solar collectors operate differently than the other collectors available on the market. This type of collectors can achieve extremely high temperature, that is 170 degree Fahrenheit to 350 degree Fahrenheit, making them more appropriate for cooling applications and the commercial and industrial applications. However, the evacuated tube collectors are more expensive than the flat plate collectors, with unit area cost about twice that of the flat plate collectors. The ETC have demonstrated and the combination of a selective surface and an effective convection suppressor can result in the good performance at the high temperatures. They are assembled in the parallel way with the heat exchanger. These solar collectors consist of a heat pipe inside a vacuum sealed tube as shown in the figure. The vacuum envelope reduces the convection and conduction losses, so the collectors can operate at the higher temperatures than FPC. Each tube contains a glass outer tube and metal absorber tube attached to a fin. Like the FPC, they collect both the direct and the diffuse radiation. However, their efficiency is higher at low incidence angles. This effect tends to give the ETC an advantage over the FPC in day-long performance. Evacuated tube collectors are efficient at the high temperatures. The collectors consist of a number of rows of parallel transparent glass tubes connected to a header pipe, and where the heat transfer fluids, usually 50% propylene glycol, is used and circulates and absorbs the heat generated by the tubes. These glass tubes are cylindrical in shape. The fin is covered with a coating that absorbs the solar energy well, but which inhibits the radiative heat loss. Air is removed or evacuated from the space between the two glass tubes to form a vacuum which eliminates the conductive and convective heat loss. The ETC are made up of a single or multiple rows of parallel transparent glass tubes supported on a frame. Each individual tube varies in diameter from between the 1 inch to 3 inch and between the 5 inch to 8 inch in length, depending upon the manufacturer. Each tube consists of a thick glass outer tube and a thinner glass inner tube called a twin glass tube or a thermos flux tube, which is covered with a special coating that absorbs solar energy but inhibits heat loss. The tubes are made of borosilicate or the soda lime glass, which is strong, resistant to high temperatures and has a high transmittance for the solar radiation. Inside each glass tube, a flat or curved aluminium or copper fins is attached to a metal heat pipe running through the inner tube. The fin is covered with a selective coating that transfers heat to the fluid that is circulating through the pipe. This sealed copper heat pipe transfers the solar heat via convection of its internal heat transfer fluid to a hot bulb that indirectly heats a copper manifold within the header tank. These copper pipes are all connected to a common manifold, which is then connected to a storage tank, thus heating the hot water during the day. The hot water can then be used at night or the next day due to the insulating properties of the tank. The insulation properties of the vacuum are so good that while the inner tube may be as high as 150 degrees centigrade, the outer tube is cooler to touch. This means that the evacuated tube water heaters can perform well and can heat water to fairly high temperatures even in cold weather, when flat plate collectors perform poorly due to the heat loss. However, the downside is that they can be a lot more expensive compared to standard flat plate collectors, as twice of the flat plate collectors cost. The evacuated tube solar collectors are well suited to commercial and industrial hot water heating applications and can be an effective alternative to flat plate collectors for domestic space heating, especially in areas where it is open cloudy. Due to the vacuum inside the glass tube, the total efficiency in all areas is higher and there is a better performance even when the sun is not at the optimum angle. The evacuative tube collectors are overall more modern and more efficient compared to the standard flat bed collectors, as they can extract the heat out of the air on the humidity dull overcast days and do not need direct sunlight to operate. For these types of solar hot water panels, the configuration of the vacuum tube is what really important. There are a few different vacuum tube configurations: single wall tube, double wall tube, direct flow or heat pipe, and these differences can determine how the fluid is circulated around the solar hot water panel. Now come to the last, that is the compound parabolic collectors. These have the capability of reflecting to the absorber all of the incident radiation within the wide limits. The compound parabolic collectors are designed by the Winston. These kinds of collectors have the ability to absorb virtually all the light emitted to the mouth of them. These collectors are able to accept a large proportion of diffuse radiation incident on their apertures and concentrate it without tracking the sun. The necessity of moving the concentrator to accommodate the changing solar orientation can be reduced by using a trap with two sections of a parabola facing each other as shown in the figure. Compound parabolic concentrators can accept incoming radiation over a relatively wide range of angles. By using the multiple internal reflections, any radiation that is entering the aperture within the collector acceptance angles find its way to the absorber surface located at the bottom of the collector. The absorber can take a variety of configurations. Here the absorber is the cylindrical configuration as shown in the figure. In the CPC shown in the figure, the lower portion of the reflector AB and AC is circular, while the upper portions BD and CE are parabolic. As the upper part of the CPC contributes little to the radiation reaching the absorber, they are usually truncated, thus forming a shorter version of the CPC, which is also cheaper. CPCs are usually covered with glass to avoid the dust and the other materials from entering the collector and thus reducing the reflectivity of its wall. The acceptance angle is defined as the angle through which a source of light can be moved and still coverage at the absorber. The orientation of a CPC collector is related to its acceptance angle theta c. Also, depending on the collector acceptance angle, the collector can be stationary or the tracking. A CPC concentrator can be oriented with its long axis along either the north-south or the east-west direction, and its aperture is tilted directly towards the equator at an angle equal to the local latitude. When oriented along the north-south direction, the collector must track the sun by turning its axis so as to face the sun continuously. As the acceptance angle of the concentrator along its long axis is wide, seasonal tilt adjustment is not necessary. It can also be stationary, but radiation will only be received the hours when the sun is within the collector acceptance angle. When the concentrator is oriented with its long axis along the east-west direction with a little seasonal adjustment in tilt angle, the collector is able to catch the sun's rays effectively through its wide acceptance angle along its long axis. The minimum acceptance angle in this case should be equal to the maximum incidence angle projected in a north-south vertical plane during the times when the output is needed from the collector. For the stationary CPC, the collectors mounted in this mode, the minimum acceptance angle is equal to 47 degree. This angle covers the declination of the sun from the summer to winter solstice. In practice, the bigger angles are used to enable the collector to collect the diffuse radiation at the expense of a solar concentration ratio. Smaller concentration ratio CPC are of the greatest practical interest. Now these are the references from where I collect the materials. You should go through these references to gather the more knowledges. Thank you.